Hello again. In the last segment on air flushing, I'll be speaking about a case study that looked at in situ air sparging, and in particular the focus of the case study was on trying to characterize the air distribution within the zone between the air sparging well and the top of the water table. This work has been published. The experimental setup in the field consisted of 3 air sparging wells and a collection of other monitoring instruments. The air sparging wells in the profile view are air sparging wells 1, 2, and 3, although air sparging well 2 was only used. And then an array of access tubes for cross borehole GPR and for neutron probe logging, and then an array of other probes for pressure measurements and other such things. However, I'll just be speaking here about the neutron probe work and the cross borehole GPR work. Again, the permeability field at CFB Borden is rather homogeneous beach sand, although it has permeability variations at the centimeter scale. So again, it's these long layered systems with very slight permeability contrast, but enough to cause a very interesting in situ air distribution. Here's a picture of the site. We removed the topsoil so that we could actually see the breakthrough of air at the water surface. Again, what we see here is bubbles being formed, but recall from the previous segment, the actual airflow within the aquifer is channel-like and not bubbles. So in this picture, we see in the background here the air sparging equipment was over here, the air sparging point is in here, and all of these other instruments in place are the monitoring access tubes for the neutron probe work and the cross borehole ground penetrating radar work. Here's another view from the back shed area where the in situ air sparging equipment was held. This is the air sparging well here and the array of access tubes and probes. One of the first things we did was, based on the breakthrough of bubbles, again they just appear as bubbles at the water surface, was to try and qualitatively describe what we were able to see. And the student who worked on this provided a scale from A to E on the rate of flow of that particular channel. A was very low or very periodic bubble breakthrough, and E was a very violent, steady stream of air. Based on that description, he was able to map the surface air channel distribution. The larger the circles, the more intense, so that would be on the scale E. The smaller the circle, like up here, that would be the low or periodic flow from that particular channel. The yellowed area here, based on the preliminary estimates we had of the site, that was the zone of influence of the airflow. So based on what we knew about the site, based on our understanding of airflow within the Borden aquifer, we estimated that that was the extent of where we would see air coming up. It's clear that although that is where the majority of the air came up, around this area here, it's clear that we had much of the airflow, although not as intense, was outside that zone. The neutron probing work was able to sense about a beach ball size zone and back calculate out of that a air saturation. So based on those data, this is a contour map, and each of these crosses here is a neutron probing logging point. So lots of data have gone into this. The air sparging point, IAS2, is in here, and based on these data, we see that the maximum estimated air saturation at the air sparging point is about 45%, and the shape of the air sparging zone is not parabolic at all, but has a lengthy or an oblong shape that aligns itself very well with the structure of the Borden Aquifer. The cross borehole ground penetrating radar, putting a GPR receiver at one point and a transmitter at the other point, the signal between the receiver and the transmitter, we relate that to how fast that returns and correlate that to the amount of air in that space. Based on those data, we can then contour a air saturation profile for cross borehole GPR work. Not quite the same as the previous neutron probe work. In this case, and based on the cross borehole work, around the air sparging point we see a air saturation of approximately 65%, and we also see this oblong shape that's aligning itself extremely well with the stratigraphy of the Borden Aquifer. You can see here that the data collected indicate that the edges of the air were well beyond our monitoring network. So what we see there then is the role of the lower permeability zones, or higher displacement pressure zones. So again, if we had dense non-aqueous phase liquids present, the air would then go around those again, pulling underneath the lower permeability zones and therefore bypassing those zones where the dense non-aqueous phase travels. With respect to mass transfer, as a result of the discrete air channels formed, there's a very small volume of the saturated zone that is contacted by air, and hence the mixing is very small. So the transfer then between the discrete air channel and the aquifer is controlled purely by aqueous phase diffusion, which is a very slow process. Under normal air sparging operations, where you're wanting to have a very high gas flow rate so that you populate a domain with a very dense channel network, you want to then, in that case, increase the volatilization rate, and that will be the mass removal process. However, if you're wanting to add oxygen to the source area or to the aquifer, then well understood operating principle is that you pulse in ambient air for a certain amount of time and then shut the system down so that the ambient air becomes entrapped within the aquifer and then will act as an electron acceptor within the aquifer. And the pulsing rate depends clearly on the ability of the system to reach a steady state. With respect to biosparging, the ambient air content in sparged air is about 20%. You could use, instead of ambient air, you could use pure oxygen, but that's extremely expensive. Or you could use peroxide to enhance the delivery of oxygen. So to conclude, even in homogeneous soils, sparge gas will quickly develop preferred pathways and channels. And most of the sparge gas will exit the water table without contacting any of the target mass at all. Point 2 is the heterogeneous elements cause gas to be preferentially conveyed to the high permeability layers, thereby bypassing contaminants within the lower permeability zones. The solubility of oxygen restricts the amount of oxygen available for biodegradation. And for some cases and in some instances, the pulsing of an air sparging system may cause the migration of contaminants away from the source area. And finally, point 5 is that the nutrients within the source area may slow down biodegradation process. So, air sparging, do you actually have mass removal, or is it just blowing bubbles in the sand? Well, that concludes the various segments on air flushing. We talked about the mass transfer process. We talked a little bit about soil vacuum extraction and a case study. And then we talked about some theoretical considerations for in situ air sparging. And then I've just concluded here with a discussion on a pilot scale experiment at CFB board where we tried to understand the air sparging distribution. So that's all for now. Goodbye.